Hey guys, so today's the day. Today we finally take this bad boy apart. For those of you who don't know, this is the Keithley 642. This is the mainframe and remote head electrometer. And this was Keithley's, and I think still is, Keithley's most sensitive electrometer they've ever made. I don't know what this thing might have been used for in the beginning. It's absolutely ridiculously sensitive. Each digit here is 62 electrons per second. So this is 10 attoamps. And you can see it's a bit noisy. It's jumping about a bit. This isn't a very good environment for this thing. It hasn't been warmed up for ages now. And you know how old electronics are. Actually, my main point of taking this thing apart is to replace the silica gel inside, because I think one of the main issues with this being a bit noisy is that the silica gel inside has dried out a bit. But I also wanted to show you inside because I've taken a look at the schematics of the thing, and I've using the user manual and with the help of a friend of mine, I've actually managed to learn quite a lot about how this thing works, and hopefully I'll be able to teach you a bit about how it works as well. Now, I don't know if you remember, but a while back I did the video on this, which is the VIB1 electrometer head, remote head for the Soviet VK216 electrometer. This is a completely different style of device. This has a dynamic capacitor inside, so it's basically got like a very weird sort of chopper amplifier, but for very small currents. It's got a capacitor whose capacitance can be varied in time by basically an electromagnet, and a very sensitive amplifier after it. So that's kind of how this thing works. This one is a pure MOSFET input electrometer, very similar to the 617. Whereas the 617 uses a JFET input, this one has a MOSFET, and this one is more electromechanical. I have a video tearing this one apart. Well, not this one, another one. I'm still looking for the VK216. Actually, I don't remember. I think this is the name of this thing, and the VK216 is the thing that it plugs into. I'm still looking for one of those, because I'd really like to try and get this one running. As you can see, this one has the biggest feedback resistor inside is 10 to the 12th ohms, which conveniently is the same as the biggest feedback resistor in this. So it's 1 tera ohm. And I know from experience that this one has an 820 gigohm and a 180 something gigohm resistor in series. It has amber dielectrics, so the support for the main terminal is amber. This one's a bit more or less refined depending on how you want to put it. This one uses sapphire, so it's got a big chunk of sapphire as a dielectric inside. This one uses amber because amber was plentiful in the Soviet Union. In theory, these are pretty well matched, so if you stick the analog output of this thing into a 4.5 digit meter, you'd get kind of the same thing. Apparently, these are actually even better than the Keithleys. I have no idea. I can't get even remotely small enough currents to verify both of them, and I have no way of measuring this one because I haven't got the read head for it. Let me rearrange this stuff a bit and I'll get back in a second. So this is the schematic for the front end itself, as I've shown you. The front end ties to the mainframe, as they call it, through a very big, very heavy, very thick and rigid cable. And that cable carries basically power, some relay states, so some digital signals for a ULN 2803 driver that drives some relays in here, and the analog output. So this thing basically, the mainframe itself is nothing more than a 4.5 digit voltmeter with some extra control circuitry inside. Now, the front end, however, the front end is a real piece of kit. So they basically pulled almost every trick in the book in order to get this thing running. It was designed in 1978. This is 47 years ago. So it's 17 years older than I am, which is insane to think about. And it's basically, an electrometer is a very simple device in practice. It's basically an amplifier with one of the inputs to ground, and the current you're measuring flows into the input, and there's a feedback resistor coming from the output. So this is plus, this is minus. Sorry, I'm drawing through the camera and it's very difficult. So all the current has to flow through this resistor and has to be yanked out of the circuit by the output of the op-amp, because there's no bias current in an ideal op-amp. So the op-amp slews its output so as to cancel the current. Now, and this gives you a meaningful voltage out. In order to get a meaningful voltage out from insanely small currents, you need a very, very low bias current for the op-amp, which is achieved by this PMOS pair, which is super weird, and a huge feedback resistor. So we have a tera ohm, 100 gig, 10 gig, and I think this is 10 to the 8th, 100 megs. All of them have some capacitance in parallel, with the exception of the two biggest ones. And you'll see that the biggest one even has a partially driven shield. So there's a shield that will collect the leakage current forming across the resistor. Usually high value resistors are encased in glass, but even glass has some leakage current, so they're usually wrapped around in a shield, and that shield is actively driven to some potential to cancel out the leakage currents. Now this electrometer can also act as a very high impedance voltmeter, in which case it only has this 100K resistor in series. It's acting as a gate protection device, and two diodes, and the feedback is basically just non-existent. It turns into a buffer, and it can also act as a basically a charge to voltage converter. So there's a capacitor in series that you can, there's a capacitor in the feedback that you can insert, and this will integrate charge over time and give you a voltage. Now again, the devil lies in the detail, as always. So we need very, 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 very low input bias currents, and that can only be achieved by a very crazy MOSFET pair. This is a super custom device. It's one of the only two. So a bit of backstory: I have a very good friend who's a professor at the university, and he told me that this is the second device that he's ever seen in his many years of doing electronics and teaching electronics that has no protection, ESD diodes or anything else on the gates of the MOSFETs, because of course it cannot afford any. The protection diodes are gallium phosphide in order to get as low leakage current as possible, but this has to be silicon to get meaningful, MOSFETs out of it. So they can't integrate the protection diodes in the silicon, because silicon has too much leakage when it's a diode like this. When it's an insulator, it's okay, because in a MOSFET, gates are completely insulated. And the other device that he saw that had no ESD protection whatsoever was a device that was integrated in an ultrasonic remote control system for a very old television set, one of the first color television sets. And it basically had a neon tube that charged the gate of a MOSFET, and the neon tube was actually driven by a resonant LC circuit that responded to the frequency of the remote control. So the remote control had an LC oscillator inside, a piezoelectric transducer that spat out some ultrasound. The TV had a receiver, and in order to remember what channel you were set, what volume you were set, it applied a voltage from that LC circuit through the neon tube to the gate of the MOSFET, which had a capacitor in series with it, or in parallel. I can't remember exactly. I'll insert the schematic somewhere. And the gate of the MOSFET had basically no leakage, so it remembered the charge basically on it. And apparently even a very old TV, like 40 or 50 years old, can still remember the settings for days. So when you turn on the TV, it's on the same channel with the same volume, and it's had a bit more functionality than that, so chroma and brightness and stuff like that. So two devices that had absolutely no protection whatsoever. Okay, so if we trace the, let me see if I can find a highlighter. I think I do have a highlighter. Yeah. So if we trace the input comes through here. It's got a very, I said there's a sapphire insulator in here. So it goes to the gate of the MOSFET. There's a current mirror here with a voltage reference and a temperature compensation for that voltage reference that maintains about 500 microamps through the sources of the MOSFETs, because these are P-channel MOSFETs. And I had some curiosity and I didn't really understand what was going on with these switches here. So you can see that they're in a half colored in bubble. And if you look here, it says denotes internal control. This means that these were set in the factory. So S102, 101, etc. are set at the factory. And what these bits do is, first of all, there's a trace here that steals away some current and drives it through a thermally coupled diode that compensates the temperature of the differential pair. And the scaling of that compensation is achieved through shorting or opening some of these resistors. And this is done at the factory. And now temperature compensation is, for a diode, so the temperature coefficient of a diode is only one direction, right? So how do you do if one of the sections of the MOSFET drifts one way or another? Well, there's another switch that can be activated that changes which side is actually the compensation is applied to. So whether the compensation is positive or negative. Same here for the offset voltage. These MOSFETs, even though they're matched pairs, they still have a various considerable amount of offset voltage. And these are all set at the factory. The offset trim, there's a very fine zero. There's a fine zero, which is a voltage to current converter circuit here that puts a current into this node, which applies a voltage, which generates a voltage across R201 here. And this R201 has the the job of compensating the last remaining offset voltage. This is the control that's on the front panel. It's this here. It's a trimmer. It's a multi-turn potentiometer. And one more interesting thing that I found about in the schematic is the rest of the schematic isn't that crazy. It's just an op-amp with an offset control as well. Here, again, a switch that compensates which side is positive, which side is negative, because if you want to do the compensation, you have to shift these things around, and then the feedback doesn't line up because you're taking the feedback off the wrong side, so you need to be able to compensate for that as well. So there's all sorts of internal controls that if you mess with, you're going to brick the thing. The feedback resistors are here, and there's one more interesting thing, which is the zero check hop compensator. So when you enable zero check, it basically shorts the input to ground. And when you do that, you inject some charge. Any actuation of a switch injects some charge, some parasitic charge into the electrometer. So what happens is when you disable the zero check, first it disables the switch here, and after a very, very short amount of time, a relay disengages as well here to extract that charge. And you can see there's a sort of a feed-through symbol here. It's just a patch of conductor wrapped around the center conductor here that extracts that remaining bit of charge. So when you're setting it to and from zero check, you don't inject or subtract charge, unwanted charge. This is the front end. There's another thing here, which is the LN2803. This drives the relays inside. And the rest of the schematic is quite simple. So we have a power supply with a 7805, a 7815, 7915, 7824. We have an intersil ICL 7103 and 82 something. So we have the logic and the analog for a 4.5 digit ADC. Have a voltage reference with an op-amp and a Zener diode, and another times 100 gain for the analog output. I have no idea why you want to use that, because it's 1 volt per 100 counts. I'm not entirely sure what it's for all the ranges, but if you have 1 volt for 100 counts and you're looking at it through a 6.5 digit multimeter, then I think you'd be in electrons per hour or something like that sensitivity, which is absurd. Like, you saw it, it's not low noise enough to give you that by default. And this thing also had the opportunity to have a GPIB board. Reps told me that his has a GPIB board. I don't know where that would connect. And you could also add an external battery power supply. So there's a switching converter that would plug in and replace basically the transformer in here. So now that we've talked for about 15 minutes about the schematic, let me take off the cover of the mainframe and show you inside, and then we can look at the remote head after I put on some gloves and clean this place out, because I don't want to contaminate the insides. I'll be right back. So for the mainframe, first of all, very cool stickers, interfaceables. IEEE 488. So GPIB. Mine doesn't have the GPIB on the back. If we look on the back, there's a fuse. This is where you'd stick in either the GPIB or the battery adapter. And this is the interconnect cable, one of those giant mil-spec cables with a lot of pins. And if we take off the last remaining screw, you're going to be able to see exactly what I was telling you about in the schematic. So we have the 7103, 8052. So this is the digital and this is the analog section of the ADC converter. Sorry, ADC, just ADC. We have a main clock and some power supply, filtering, transformer, and stuff like that. Nothing absolutely remarkable in here. That's basically just a single voltmeter circuit with a bit of extra gain. Okay, now we shall go to the exciting part. Give me just a few minutes. Okay, so in order to take apart the electrometer, so first of all, I cleaned the surface a bit, and we have some 5/64 screws and this one, which I have no idea what it is. I forgot they're both Imperial, and there's also some Phillips screws on the back. So we're gonna start with those. And this is where my heart starts racing, and these are clean nitrile gloves. The tools are clean. The table is clean. My soul is clean. My thoughts are clean, etc., etc. So I'm doing the best I can. Oh, I'm also grounded. I have a ESD strap on my leg that goes to the ESD top as well. So I shouldn't kill it. So on the bottom, we don't really see much right off the bat. But if we take a small flat head, we can peel off this bit here and we can see the beginning of the circuitry inside. So this is the a part of the adjustments and part of the circuitry that goes deeper into the device itself. And that's about it. Now, for the rest, we're gonna need Imperial stuff. Gosh, I hate Imperial tooling. I have no idea why. I mean, this thing is 50 years old, made in the United States. Makes sense. And I hope that everybody moves away from the Imperial system and adopts the one and only metric system. Because, you know, the joke with there's two types of countries in the world: countries that use the metric system and countries that put the man on the moon. Well, NASA used the metric system, so shots fired. Why would you say 50 millionths of an inch per foot when you can say 10 microns per meter or something like that? I think it's really stupid. Okay, I lost some washers, but I remember them and I'm gonna put them back. And now we can take off. Oh, Jesus, tight. Oh, this is the main input. That's the sapphire. And the gold thing is the actual contact, and this is the shield. And these are quite tight as well. And let's see. Don't want to use any power tools next to this thing. I don't want to risk it. By the way, do you know that in kitchens, in professional kitchens, when they were forced to use gloves, it turned out that they were being less hygienic than without using gloves, because they thought that gloves are some cure-all for everything that means dirt and stuff, and they wouldn't wash their hands. So you can see that huge thing over there. Let me zoom you in a bit. That is the main MOSFET pair. I don't recognize that symbol, but you can see just how big the thing is. And let's see how we can take out more of the stuff from here. So I'm assuming it's these flathead screws around here. Let me see if I have a flathead around. Yeah, I have one of those stubbies. Whoops, this was loose. This has been tampered with in the past. Huh, this is also loose. Oops, that's weird. This one is also loose. What the hell is going on here? I promise I didn't go through this and loosen the screws before. You have no dexterity when you're wearing gloves. Okay, and I think also these need to come out. This is the main input tube and stuff. I'm trying not to touch it as much as I can, although I'm reasonably clean. Apparently amber is better dielectric than sapphire. That's what I heard. Although I think it's a bit more piezoelectric. I still have some of those amber components out of the weird Soviet electrometer thing that I took apart a while back. Okay, I think it's coming. Oh boy. Oh boy. Holy poop. Okay, let me figure out how I'm gonna hold this thing while I show it to you, because I want to minimize my contribution to this thing's situation as much as possible. So we have some huge resistors here. We have all the manipulators, the relays. These things actually contact the inside of the circuitry. So the inside of the tube, that's where they make contact with the internal conductor. Oops, this thing is a handful. Wait, I think I can unplug this. Yeah, and I can loosen this thing up and it will be detached. Okay, so we have the main MOSFET pair, and we have the switches, the control for all the feedback resistors. And you can see the feedback resistors are those giant tubes. That one is 100 megs. That one is, I don't know what it is because it's not really visible. I think these are all metal oxide resistors. I'm not entirely sure about that. And yeah, and the relay. I don't know what that relay does. What it really does. But yeah, oh gosh, another loose screw, what the heck. Someone has been inside this thing before me. Yeah, so again, one last time, before I put this thing back together. Input MOSFETs, capacitors, the protection diode is somewhere inside as well, so in the tube, somewhere in there. And all the relays, all these solenoids do is move the various contacts and establish the various feedback topologies. Gorgeous, absolutely gorgeous piece of kit. And it's a ULN 2003, not a 2803 as I thought initially. And maybe we can take a sneak peek underneath this cover here. Find a screwdriver. It's very hard to take apart stuff when you're looking through the camera. Hopefully I'm not doing some irreversible damage to this thing. Although, if I ever see screws... This one was loose as well! What the heck is going on? Yeah, so let's look inside. That there is where the leg of the MOSFET connects. And those are the different feedback things. Okay, I'm gonna put it back. I think you've seen enough. All of these switches are the internal controls that I mentioned. And of course there's an NE555 timer in here for the WAN. This has to do with the hop correction, the thing that I explained. Okay, let me put this thing back while I'm not looking through the camera and we'll discuss. Wait, I just realized a few things. So this is the zero hop correction. This is the terminal that injects some charge when you're disconnecting. So when you're disabling the zero cross zero check. And this trimmer is the thing that sets how much charge it's injecting or rejecting or extracting. And this terminal here, the first one, this one here is the MOSFET gate. And this one here is the gallium phosphide diode. And I think it's pretty hard to see. I don't know how I saw it. Yeah, it's here. You can see it just there. So that's the super low leakage diode. You can just barely make it out underneath the MOSFET. And underneath the MOSFET should also be, yeah, so that diode there is the temperature compensation diode for the MOSFET, the entire circuitry that I was talking to you about. Okay, now I'm going to put this thing back together and we can talk about it later. Also, tantalum caps, I'm going to leave them. I'm not going to bother them. Be right back. One more thing, I promise. Matched transistor. So this is the current mirror, and this is the voltage reference, and this diode, along with this diode here, compensate the temperature of the temperature coefficient of the current mirror. So this is what injects current through the transistor. This is the entire row of compensation that we saw. These switches select the compensation. These are fine trims, and this is the main op amp. Yep. Okay, that's it. I'll put it back together. Okay, so let me zoom in a bit, and we're gonna take one more look over it in its entirety. So we have the coil driver, we have an op amp, we have the 555 timer that does the zero check hop thing. We have the feed through that actually connects, so this point feeds the positive or negative charge into the front input of the MOSFET. We have the current mirror with its associated voltage reference for generating the reference current and temperature compensation. We have the offset voltage compensation and the temperature compensation scaling. This is direction, so compensating the tempo and compensating the offset voltage, the direction which you want to compensate those. We have the main connector towards the output, so to the outside world. This ties in straight through to the big military mil-spec connector on the back. We have the actuators. These are just actuators, they're not relays. The relay end of them is formed inside, where a gold-plated thing touches another gold-plated thing like this. So basically the resistor to be inserted in the feedback touches the input terminal like this. This is what the motion that these things are doing. And I realize now that this is the this Koto relay here is the zero hop, zero cross detect. And this other relay, if we look on the schematic, is K109. So K109, which has a lot of poles, is the zero check itself. So this is the charge injection, and this is the zero check itself. Cool. Super cool. Absolutely wonderful. Imagine people who are assembling these things. Isn't that just gorgeous? Like, how beautiful is that of a circuit? I'm gonna let you bask in its glory for a bit. And that sapphire insulator. And you can see inside those gold-plated things, those are the things that connect the feedback resistors to the input. Okay, I'm going to put it back now, and we'll talk about it a bit later. What do you think? I would break it? So this is, in its language, it's 0.1 times 10 to the minus, no, it's it's 0.1 times 10 to the minus 8th amps. In regular speak, it's 1 nanoamp. So that was not fun at all, putting it back together. I mean, the thing itself is very fun. By the way, measuring anything lower than this, like if I go to 10 E minus 8, I should be fine. Yeah, 10 E minus 8. That's 100 nanoamps. It's fine. Anything lower, I just don't have the right stuff to measure it with. It's very accurate as well. Like, it's only 14 pico. No, I have no idea what that is. If this is 100 nanoamps, this is nanoamps, this is 100 picoamps, and this is 10 picoamps, so I'm 140 picoamps off. I think 140 picoamps off is just either it not being up fully warmed up, although the zero check is pretty good, or just this cable, because moving it around is like another 10 picoamps out of the blue. So I'm gonna quit while I'm ahead. It's still wait for it. It will come back to normal. If I hit zero check, it's pretty good. After it warms up, it'll go back to being okay. This is regular behavior. I didn't do anything to it in any way whatsoever. Zero check still works. Yeah, everything is totally fine. Anyway, I hope you liked seeing inside this beauty. It's super weird, super interesting, completely useless, but these things still fetch a very, very high price on eBay. By my opinion, it's a price that doesn't make any sense, because what are you going to use this thing for? Anyway, thanks for watching. See you next time. Bye.